Welcome to this session. This session is on thermodynamics, not to be confused with thermochemistry. So it is my advice to you that you have listened to the thermochemistry, or at least have a good background in that from your classroom before you get yourself all confused and out of whack by putting the cart before the proverbial horse. My name is Renee McCormick, and as you can see by the logo on this document, I am from the National Math and Science Initiative and happy to be with you here on a Friday afternoon. While most people are getting ready for a weekend, no, not me, geek that I am, I have elected to talk to you about the second and third laws of thermodynamics. The thermochemistry chapter that we've already covered actually deals with the first law of thermodynamics quite extensively, I must say. So we're going to touch on the second and third laws as we go through this unit. There's a lot of algebra in this unit and a little bit of abstract thinking, but I can comfort you right away by saying that if you can do some 8th grade algebra, and if you have a messy room at home, you'll understand this quite nicely. So essentially what we're going to do is try to tie enthalpy, delta H, our good buddy delta H, to entropy, and both of those to delta G, which you were exposed to back when we were doing electrochem, if you did electrochem early in the year. And so now you're going to get to understand these things a little better, and it's not a bad idea to go back and review as we go along and build on these concepts, and the concepts start to overlap and tie together. It's a good thing for you to go back and review a bit that you might have been a little fuzzy on when you took the test back in that unit, so that you can get a nice clear picture of exactly what's going on here. Alright, so what is it exactly that drives a reaction to be spontaneous? We do use the phrase drives a reaction quite often, and overwhelmingly there are two concepts that drive a reaction. There are many other smaller factors, but overwhelmingly the two big ideas are the enthalpy and the entropy. So let's talk about each of those terms. The enthalpy, which is our delta H term, is the heat content, and generally exothermic reactions are favored. And entropy, which is the disorder of a system, which is symbolized by delta S, is often driving the reaction because the more disordered state is favored, which is why I said you would understand this, because no matter how hard you try to keep your mother happy by keeping your room all nice and clean, which includes your sock drawer, I suspect life happens and it doesn't become your highest priority to make sure that your sock drawer is completely organized. So I think you've already accepted the fact that nature works against you and that a disordered state is often favored. So nature tends toward chaos, and what I need you to think about in a chemical sense when we say chaos is that nature favors a less condensed state. And what I mean by that is the states that are favored, solid is very organized and least favored compared to liquid, or compared to the most disordered, which is the gas phase. And aqueous can fall somewhere in between liquid and gas in terms of there are actually some aqueous systems that, because of the way the water interacts with the dissolved ions, it may bring more order to the system. But essentially, if you lock onto the fact that enthalpy and entropy are driving this, and that exothermic is favored and entropy such that the disorder is increasing is favored. So that's a positive delta S, whereas this would be a negative delta H. This would be a positive delta S. So spontaneous reactions, as we define them chemically, thermodynamically, shall we say, are those that occur without any outside intervention once the energy of activation has been reached. And thermodynamics also, needs to be very clear to you, does not predict or take into account the rate of a reaction. It cannot predict it, cannot take it into account. That's what we studied kinetics for. So if you've already studied kinetics prior to arriving here, then you can rely on that kinetics knowledge. Otherwise, it's probably the next unit you're going to cover if your teacher's following the NIMSY sequence. So some reactions are very fast, like the combustion of hydrogen once their activation energy is met, and other reactions are very slow once their activation energy is met, such like the graphite turning into diamond. It is, however, thermodynamically spontaneous. It's just awfully slow. And so what's the scoop on just some general ideas before we leave this little section? Well, if you consider an element versus a compound, which do you think is more thermodynamically favored? Well, it's going to be the compound. How come? Well, when the compound is formed, then bonds are made, and we talked about that in the enthalpy chapter, and when those bonds are made, that means that energy is released, And so if we have that exothermic situation, that means that more energy was released than it took to break bonds of anything that was reacting to form that compound. So that's important. And like I said, the first law of thermodynamics was the subject of the first recording on thermochemistry. The second and third laws of thermodynamics, with the second one being far more of a time hog, shall we say, in this chapter, is going to be our focus. But I need to point out to you that there's also a zeroth law. I know that sounds like the dumbest thing you've ever heard. So you know what happened, right? This stuff doesn't always get laid out in order in science, you know? Like when you studied photosynthesis, there was photosystem 1 and photosystem 2. We named them that way because that's the way we think they evolved. But guess which one acts first? Yep, photosystem 2. So it doesn't make sense sometimes. So we kind of figured out the first law, second law, third law, and then went, you know what, there was something incredibly obvious that needed to be stated that no one stated, so we have to go back and now call it the zeroth law. And it's one that's going to make you feel good because you're going to embrace it immediately. If substance A is in thermal equilibrium, that's supposed to look like thermal, with substance B, and B is in thermal equilibrium with object C, you guessed it, object A is thus in thermal equilibrium with object C. So I've never seen an AP chemistry test question on that, maybe a physics one, but you need to know it nonetheless, just so you can say you've heard of that before. And it's kind of silly and sort of fun to remember. But we're going to focus on a more practical law of thermodynamics, which is the second law of thermodynamics. There are many ways to state it. One way is to say that the universe is constantly increasing in disorder. Another is to say you can never break even. You're always going to pay the universe something, because how else could the universe constantly be increasing in disorder? And a gentleman named Rudolf Clausius, I believe is how you would say that's how I was taught to say it anyway, and you'll hear a lot about him later when we study vapor pressures in a different unit. He discovered this second law of thermodynamics, which means he really was the first sort of to state it, and an argument could be made that it might have been Gibbs as well, but he gave it its symbol. So it's his fault that entropy is symbolized by an S when an S is not in the word entropy. We're also going to talk about the third law of thermodynamics, which states that the entropy of a perfect crystal at 0 Kelvin is 0. So it's a much simpler, straightforward law. There are not a lot of perfect crystals out there, so that entropy value is rarely ever 0. So even for elements, because elements are not at 0 K, that means their electrons are not completely still, and that means their electrons are zipping around out in the electron cloud, so thus they have their own degree of disorder, so they do not have 0 as their value. So when we were working delta H problems, we celebrated when there was an element in our chemical equation because, woohoo, it's delta H if formation was 0. And when we do delta G later in this chapter, we'll celebrate again. Woohoo, if it's delta G of an element, then its value is 0. But, aw, shucks, if it's delta S, we have to look it up. So what it really means is that the absolute entropy of a substance can be determined at any temperature higher than 0 Kelvin. So we're a fan of 25 Celsius, which you know is 298 Kelvin, so you'll see that a lot. So this is a really handy little statement to use if you find yourself having to write about why G and H for elements are not equal to 0. Are equal to 0. I said that backwards. They are equal to 0, but S is not equal to 0. Again, it's because it's got electrons and it's not at 0 K. Thus, those electrons are moving. Now, entropy, the big idea on the molecular scale, is about all the different possible arrangements that molecules in a system could have. So this little diagram is just kind of showing us what we call microstates, and it's saying, well, if we had 4 entities, 4 molecules in the system, then they could all be over here. Conversely, they could all be over there, right? Or we could have 3 in one spot and 1 in the other, and we could flip that around as well. Or we could have 2 in each and flip that around so that it wouldn't be the exact same 2. And so this is just kind of getting the idea across that the more electrons that we have, the more molecules that have electrons within them that we have in a system, the more disordered the system. And then, of course, the warmer the system is, heat 'em up, speed 'em up kicks in. Because now not only do you have just electrons that are constantly moving, but you got electrons that are moving pretty dang fast. So the greater the disorder or randomness in a system, the larger the entropy. So you need to lock on to the idea of that disorder and entropy are synonymous terms in a way. They go hand in hand. If the disorder increases, the entropy increases, and vice versa. So the entropy of a substance always increases as it changes from solid to liquid to gas, because what's the scoop on solids? You have fixed molecules or atoms, and they are fixed into a position, and all they can really do is vibrate around that point, that fixed point that they're locked into this crystal with. But if you melt them, then they start to acquire some translational motion, which means go from point A to point B. And they also can be free to rotate once they're unlocked, I should say, from that crystal. And then, well, chaos abounds in the gas phase. They're going bing, bing, bing all over the place with theoretically no attraction to each other. Liquids are at least still attracted to each other, or they wouldn't be liquid. As soon as they lose those attractive forces, they vaporize and become a gas. So big jumps in entropy, easy for me to say, when you go from solid to liquid to gas. So when a pure solid or liquid dissolves in a solvent, this is where it gets a little tricky. Normally the entropy of the substance increases because you went from this rigid solid crystal like in an ionic form to now free-floating charged ions that can actually conduct an electric current. That's why we call them electrolytes. But sometimes that rule is sort of violated, and carbonates are one of those sometimes. Carbonates actually interact with the water because the water is very attracted to them. So when the carbonates dissolve, they actually organize the water fairly well, and they can bring more order to the system, and so the delta S may actually drop, which is counterintuitive. You'd think it would go up. So be on the lookout for those exceptions. Because, you know, you've heard me say before, first year chemistry, we teach you all the generalities. Second year chemistry, we pretty much torture you with the exceptions. So item 4 here on my list is when gas molecules escape from a solvent, the entropy increases. Entropy generally increases with increasing molecular complexity. We talked about that a second ago. The more complex, that means the more atoms, molecules, ions, whatever fits, but ultimately they all started as atoms. So the more atoms you have, the more electrons you have, the more chaos you have, more disorder. Now, some review books oversimplify that, and you could lose points on the AP exam when you're writing about this. You can think this, but you can't write this. I've even seen it written in textbooks before, where it says increasing molar mass increases entropy. That's an oversimplification. It's not because the molecules are heavier. It's because with increasing molar mass, which is primarily more protons and neutrons, electrons come along as well, you have more electrons. It's really the electrons that are the culprit in increasing the entropy. All right, so reactions increasing the number of moles of particles often increase entropy as well. So even if you have a liquid becoming, let's say, dissociating into 2 more liquids, just start getting in the habit of looking at moles on the left, moles on the right. And then look at the states. Moles of what on the left? Solid, liquid, gas. Moles of what on the right? AP is a big fan of you discussing the fact that more moles of gas were formed, more moles of liquid were formed than existed in the reactant state. So in general, the greater number of arrangements, the higher the entropy of the system. You knew that calculator was there for a reason, didn't ya? All right. So we are going to predicting entropy changes. So we'll start a little qualitative at first. So predict the sign of the entropy change for each of the following processes. What do you think? Solid sugar added to water to form a solution. Now, what sugar do you figure they're talking about? I think they're talking about the one on the table, which is going to be sucrose, which is going to be C12H22O11. That's a whole lot of electrons in all of those atoms. But you've seen sugar before. And what happens when sugar is added to water? It dissolves. So instead of being in this big giant clump of molecules in a crystalline form, that's why sugar is shiny, it refracts light fairly well, you're going to now have it in a more dissolved form. Note I did not say ionized because this is a big giant hydrocarbon. It's going to make a molecule. It's not going to split up into charged pieces. So I would predict a positive delta S, as I'm sure you did. Iodine vapor, Okay, let's talk about the difference between vapor and gas. And I'm going to keep talking about it until you get it. Vapor is a word that's used to describe the gaseous form of something that is normally not a gas at room temperature. So at room temperature, iodine, diatomic, right? It's a halogen. All the gens are diatomic, hydrogen, oxygen, nitrogen, all the halogens. So normally it's a solid. It's kind of a shiny purple crystal. But if you warm it just a little bit, it jumps all the way to vapor. It skips the liquid phase. What's the word for that? Oh, come on. I know you know it. Come on. I know it's rolling around in your head. Yes, it sublimes. So iodine vapor condenses. So this is really the reverse of that reaction. It condenses. So condense is your friend. All right, because increases in entropy make a less condensed state. So when it says something condenses, you're going against the entropy. So it's going to go from the vapor phase to the solid phase because it's going to form crystals. They never use the word solid, but you know that crystals are solid. So this is going to be a drop or a decrease in entropy. So in this case, it's going from gas this direction to solid. It's going from incredibly disordered down to very, very ordered. Okay, so just like we calculated delta H and such things from tables, we can also calculate all of the S's as well as G's, as you're soon to learn. So we can calculate entropies and free energies from tables of values. This one's still asking you, though, to just kind of figure out which one has the largest increase in entropy qualitatively. There's no numbers to crunch here. So what do you figure? Pause me, try this, come back. We'll talk about it. I'll wait. Welcome back. All right. I've got a solid to a gas. What do you figure? Definitely. Skipped way through the liquid phase. I'd say that gets 3 stars as an increase in entropy. 3 pluses. All right. So what do you figure now? 2 moles of gas on the left, 2 moles of gas on the right. You had these little elements. You had this now fairly small molecule. That is almost a wash. Without some numbers to crunch, I can't really make a comment other than delta S is really close to not changing at all. So I'm going to say it's approximately equal to 0. Then I have solid to liquid. What do you figure? If solid to gas got 3 pluses, I'm going to give solid to liquid 2 pluses. It's definitely going to increase its entropy, but not as radically from solid to liquid, that's just melting, as solid to gas, which is vaporizing. And now I've got diamond and graphite. Oh, we're going to see if you know much about just what we call descriptive chemistry now. I'll bet you know the state of matter that a diamond occupies. Multiple choice question. A diamond is A, gas, B, liquid, C, solid. I know a lot of women that would be very depressed if it did not stay in the solid phase. Or what about graphite? Yeah, you've used graphite. You use it a lot. Where do you use graphite? Your pencil. Lead, in quotes. It's not lead. That would be stupid, because if you cheat on your pencil, you'd acquire toxic levels of lead and be brain damaged. No, you can't use that as an excuse when you fail your next test. But this is also a solid. So I've got solid to solid. But the difference is diamond, every single carbon in diamond is tetrahedrally bound to its neighbors. So it makes a bond with, it's called a network solid. It makes a covalent bond with each and every one of its neighbors in 4 directions. Graphite makes bonds with its neighbors as well, but it only does it in 2 dimensions, not in 3 dimensions. And so that's what lets you do this with your pencil lead across the page, and it just shaves off a layer of graphite and leaves it behind on that piece of paper. So this one is an increase in entropy, but not so much. So that was just a ranking task, and we love to do those little Roman numeral questions in multiple choice and ask you such things. So get your head wrapped around those concepts before we dig into the math here. So back when we did the first chapter on thermochemistry, I told you about Hess's law. I also told you I call it the Big Mama equation, because we had this equation in the form of delta H of the reaction, and I can put the 0 on there, the naught, to imply standard conditions, 1 atmosphere, 25 degrees Celsius, which equals 298 K, 1 molar solutions. All right, so delta H reactions is going to equal the sum of the delta H of the products minus the sum of the delta H of the reactants. That was verse 1 of the Big Mama equations. I call this one verse 2 with the S's. Look, if you learned verse 1, you get verse 2 for free. It just deals with entropy naught instead of enthalpy naught. So obviously, S is going to be positive when disorder increases, which is the favored state. Think of your room. S is going to be negative when disorder decreases, because the universe is going to have to bring order back into that system. And wouldn't it be nice if that happened in your room and your mother wouldn't yell at you or ground you? So units are usually joules per Kelvin mole. Now this is tricky because G's and H's are in kilojoules. So the bottom line is it's not as big an energy difference. It's off by 3 orders of magnitude. So you are going to have to be on the lookout. So I always told my kids, look, it starts with S. So aw shucks, you still have to look out for the units on S. You also have to look out for the fact that S of an element is not going to be 0 unless it's a pure crystal at 0 Kelvin, which ain't going to happen. All right, so this is just a Big Mama moment. So they want us to calculate the entropy change at 25 degrees Celsius in joules per mole Kelvin or Kelvin mole. You're going to see me write it both ways throughout these notes, partly because it was just an accident, I'll admit that. But also, it doesn't matter. It's a commutative thing. 2 times 3, 3 times 2. That little dot means they're multiplied together. Okay, so what do we have here? We have delta S of the reaction at standard conditions, S naught, sum of the delta S naughts of the products minus the sum of the delta S naughts of the reactants. What does that look like? Look at your balanced equation. Product 2 times the SO3 minus 2 times the SO2 plus an O2. And then I like to look up there and get the numbers. I know you don't want to do that step. I know it just violates everything in your lazy little teenager body to even think about doing it. But I'm telling you, you're going to make fewer mistakes and you'll be glad. I know some of you won't believe me and you'll goof this all up and then you'll come back to believe me. All right, so this is going to be 2 times, this is the SO3, so it's the 256.6. And I'm not going to put units in this calculation because I know they're all in joules per mole Kelvin. I can slap that on at the end. I will let you be lazy about that at the moment. So 2 times the SO2 is 248.1 plus, unfortunately, that's not 0. Matter of fact, it has a substantial value compared to the rest of 205.3. So I like to push it in my calculator exactly as it looks on the page and not get creative because I don't want to mess up any of my signs. So 2 times 256.6 minus, open a paren, 2 times 248.1 plus 205, so I wrote 250. Dang it. 05. Try third time's a charm. 05. There we go. 0.3. Hopefully I punched everything in right. And I come out with a negative 188.3. Whew, love it when I get the right answer. A negative 188.3. Now, what are the units again? Just look at the table. Joules per mole Kelvin. Or Kelvin mole, whichever. Box your answer for good form. Delta S naught of the reaction. Now, does that make sense? That's what you always want to ask yourself. Does that make sense? Yes, it does. Because look, 3 moles of gas going to 2 moles of gas. Expect a drop in delta S. Okay, you've got to expect it. So yes, a minus sign makes perfect sense. Also note that these are all positive. Again, why? Because they all have electrons. Who has the most? Well, that'd be SO3. Who has the highest value for entropy? Ha! See, I'm right. Who has the next most? That'd be SO2. Who has the next most highest value for entropy? Ha! See? It works that way. I wouldn't lie to you. Okay. Next concept. Entropy changes for reversible phase changes. Okay, reversible phase changes is code for equilibrium. And at equilibrium, delta G is going to equal 0. I want you to lock onto that now, even though we're going to talk about delta G in more specifics later. If you've done electrochem, you already know this, right? What else do you know? You also know that at equilibrium, the K value is equal to 1. So just kind of reminding you that you already know some of this stuff. So a phase change is always going to have these double arrows if the people typing it typed it right, and I'm going to have to check myself as we go through this. All right, so delta S naught is defined as Q over T, which translates in English to the heat transferred divided by the temperature at which the change occurs. And it's expressed in, as you just saw, joules per mole Kelvin. So where the heat supplied endothermic with Q greater than 0, or the heat evolved if it's exothermic with a Q less than 0, which means minus, which means plus. Sometimes I don't like the Q greater than less than 0 business, but you get it, is divided by the temperature in kelvins. So it's important to note here that if the reaction is exo or endo, you got to pay attention to your signs. And the actual significance of this is really dependent on the temperature at which the process occurs. Now, what this is trying to say to you is that unlike delta H and delta G, delta S actually has a temperature term in its definition. The best analogy I've ever heard about this in terms of a change in S, you're going to get different changes in S's depending on whether the system was hot or cold to begin with. So you can't ignore where it started. So for instance, if you were out on a busy street corner and it was horns honking, there were people everywhere, think like New York City, or if you're a romantic, think like Paris. But, I mean, it's the hustle and bustle of a big city. And you sneeze as you wait for the light to change so you can cross the street. Are you really contributing much to the chaos of the surroundings with that little sneeze? Even if it's a big old loud honking sneeze? Probably not so much. But now let's go to a different environment. Let's go inside a building. Let's go up the stairs. Let's go into a very quiet space in a library where everyone there has their nose in a book and is being incredibly productive. So no one is talking. There's no one getting up running around. There might be somebody going up to get a different book, but that's about the only activity in the room. Now you let out a sneeze, whether it is petite and delicate and dainty, or whether it's a big old honking sneeze. You're going to create a lot more disorder in that environment than you are if you're on that crowded street corner. So you got to think about temperature in terms of how temperature is actually defined. Temperature is proportional to the average kinetic energy, and kinetic energy is defined mechanically as 1/2 mv squared, where v is velocity. So the hustle and bustle of the street has a lot more velocity. So you're not gonna make as big a splash, shall we say, in changing the entropy of the system when you're in the system and you sneeze on a street corner versus sneezing in a quiet library. All right. So just conceptually, that's all that was trying to explain to you. So we're going to take favored conditions into consideration, and this is how we literally define delta S. So when we talk about one of these phase changes, when we talk about water liquid at 100 degrees Celsius and water gas at 100 degrees Celsius, by the way, when phase changes occur, you stay at the same temperature. That's another lesson in another chapter. You can dazzle your parents with that newfound knowledge. When water is boiling, the temperature is not changing. My mother always thought it was. I had to prove it to her with a thermometer when I learned this as a sophomore in high school. I took great pleasure in that too. So entropy is going to increase, but your temperature isn't. So when we look at this system, we have to think about that. So we're going to give signs to delta H following those exo, minus, endo, plus, exit, left, endo, entered, guidelines. So let's look at this one. In the metallurgy of antimony, which is one of my favorite symbols, SB, the pure metal is recovered via different reactions depending on the composition of the ore. You know, we dig up stuff. We dig up rocks and ores, and then we have to take them back to the lab and purify them to get the actual metal out of them. It's what mining is all about. So, for example, iron is used to reduce antimony in sulfide ores. So carbon is used as the reducing agent for oxide ores, and we want to calculate the delta S surrounding for each of these reactions at 25 degrees Celsius and 1 atmosphere. So we'll do number 1 first. Delta S of the surroundings, not the system, is equal to minus delta H over T. Well, look back at these definitions. If delta S is Q over T, then this is from the system point of view. This is from the surroundings point of view. We put the minus sign on there. All right, so now that's minus 125 kilojoules, because they told me that, it's sitting right there, divided by, what's the temperature? 25 degrees Celsius. That's 298 Kelvin. And this really should read per mole, and this should read per mole. They're not telling us it isn't, so I'm going to assume that it is. Keep my units straight. So I get negative 125 divided by 298. And I get an entropy change in kilojoules. And that's going to be a positive. Oh, I left that negative sign off. This value is negative. I knew it was supposed to be positive. How did I know it was supposed to be positive? It's kind of hard to eyeball this one because everything's in the solid phase, but positive 419, is that what I got? Yeah, 419 joules per Kelvin mole. And no, it wouldn't be wrong if you'd have written it like it is in my calculator, 0.419, and left it in kilojoules per Kelvin mole. But I'm telling you, when you start looking these up in the tables, this is what it's going to be reported as. And I want you to get used to it. Looking out for you. Okay, number 2, the delta S of the surroundings is equal to minus delta H over T. And I'm not going to forget my minus sign this time. And this delta S is a positive 778 kilojoules, and still we're at 298 Kelvin. That should still be per mole. So 770 minus 778 divided by 298 is a negative 2.611. Just go with 3 sig figs because they gave me 3 in those numbers up there. Kilojoules per Kelvin mole. All right, so carrying on, let's summarize entropy before we move into the next concept. So I think you get it by now. If you don't, then that's what the rewind's for. So delta S is positive if we have more disorder, which is the favored condition, and that's important for you to know, favored condition. And delta S is negative, meaning there's less disorder. More order, if you like to think of it that way, but I like to stick with one word. It just makes more sense in my brain, but if you don't get mixed up, that's fine by me. So what we're really saying is the things that we're really looking for, and I'm telling you what I'm about to show you right now is going to translate into a whole bunch of multiple choice points. Fewer moles of gas, going to more moles of gas, positive delta S. Solid, going to liquid, going to gas, positive delta S. And you can reverse that. Go that way and that way, negative delta S as we move back from left to right. And nature prefers a less dense state. And that's going to be an increase in entropy, because we have that law that says the entropy of the universe is always increasing. So whether a reaction is going to occur spontaneously or not can be determined by looking at the delta S of the universe, just the sum of the delta S of the system plus the delta S of the surroundings. And if the delta S of the universe is positive, the reaction is spontaneous. If it's negative, the reaction is non-spontaneous. So we have an example. A good buddy, hydrogen gas plus oxygen gas yielding water. If we ignite this and give it a spark to get over the activation of energy hump, then the reaction is spontaneous, and consequently it's very fast, but thermodynamics would not tell us that. This fast business is all about kinetics. This is just an observation at this point. So the delta S of the system decreases, as you would expect if it's a spontaneous reaction. And I'm not telling you that's the only indicator, because delta H is also an indicator, but it is a indicator. So it's a negative 88.9 joules per Kelvin mole. So the entropy declines. If you were asked to explain why, I hope you would go back to moles of gas on the left, moles of gas on the right. 3 moles of gas on the left, only 1 mole of gas on the right. So that's a more condensed, more ordered state. So the entropy dropped. So we put a negative sign on it. All right, so this then goes on to go ahead and calculate the entropy of the surroundings. So the delta S of the surroundings would be the Q of the surroundings, which would come from a delta H calculation I'll spare you, that comes out to be negative 483.6 divided by T. So the first law of thermodynamics would demand that if this delta H is negative for the system, it would have to be positive for the surroundings, because energy is never created nor destroyed. It only changes form, so what's lost must be gained somewhere else, because you can't just have it evaporate. So my minus 483.6 is now becoming a minus again, so thus it's going to become a positive value. So the delta S of the surroundings would be that positive value over the temperature 298 Kelvin, and I come out with this amount of joules per Kelvin mole. So now we can find the delta S of the universe by taking our 88.9 joule per Kelvin mole. Units are driving me crazy in this unit. Haha. All right, and then add it to the surroundings, and we come up with this. All right, so even though the entropy of the system declined, the entropy change from the surroundings was so large that the overall change for the universe is still positive. So bottom line is we got to obey that law. So a process is spontaneous in spite of a negative entropy change as long as it's extremely exothermic. So this phrase is something you may have to, you will find yourself writing when we start working through free response problems. Sufficient exothermicity, no, I did not make that word up, it really is a word. Sufficient exothermicity offsets system ordering. Because you're about to enter the land of Gibbs free energy, and this is what we're going to do, is we're going to calculate with these things. So free energy, I'm now switching gears. Keep up with me or pause me and go take a break and come back, but free energy is delta G. And if I put the naught on it, we're talking standard conditions. So Gibbs free energy, and no, this is not the Bee Gees. This is not one of the Brother Gibbs. This is nothing about Saturday Night Fever. This is about Wilbur Gibbs, who actually I believe was the first American to ever win a Nobel Prize in chemistry, but don't quote me about that. You may have to look that up and confirm it. But I think I'm right. So calculation of Gibbs free energy is what's ultimately going to decide. So what delta G does is it addresses both the enthalpy that we talked about in the thermochemistry chapter and the entropy that we've talked about thus far here. And being that the entropy is temperature dependent, we have a T term thrown in that we have to multiply by the delta S. Crowded street corner, quiet library. The state of the surroundings with regard to temperature and energy related to the energy of the molecules matters. All right, so the signs are the same that you saw in electrochem. If you have a negative delta G, that translates to spontaneous, because energy is leaving the system. All right, so I call it Big Mama verse 3. If you've given a table of values, then the overall delta G of the reaction is the sum of the delta G's of the products, you guessed it, minus the sum of the delta G's of the reactants. Works the same way as enthalpy, works the same way as entropy. That's enthalpy's verse 1, entropy's verse 2, and this is verse 3. These are things you do not write on the AP exam. You do not talk about Big Mama. You do not say anything about verses. You stick with the symbolization of what this is, Hess's law. Then delta G, I've got good news for you. Delta G formation is 0 for elements the same way delta H formation is equal to 0. But delta S formations, because the electrons are not standing still, is not equal to 0. So aw shucks, you gotta look that one up. All right, so we put all this information together and we get one of the most beneficial equations to learn for the AP exam. Lots and lots of points are tied to delta G equals delta H minus T delta S. We can also do this through systems of equations like we did with enthalpy, where I have chemical equations and I may have to reverse one and change the sign on its delta G and that sort of thing. And so I can do that same song and dance with delta G's as well. So now what's kind of fun is to kind of analyze that delta G and equilibrium are actually connected. So this equation is usually called the Gibbs-Helmholtz, it's hard for me to say, equation, which is a hyphenated name, meaning two scientists worked on this together. And they basically figured out that Q, the reaction quotient, which means you may or may not be at equilibrium, your Q equals K only when you are at equilibrium. So Q can be greater than K or less than K depending on which side of the equilibrium you're on. Are you headed in the forward direction where your reactants are still reacting to make products? Or are your products slamming into each other and undoing that and headed back to the left side of the equation? Because with equilibrium, you get these double-edged arrows. It's a reversible reaction. So let's just define our terms. Delta G is free energy not at standard conditions, hence the lack of a naught, the zero, an NaUGHT. Delta G with the naught, NaUGHT is what my Texas tongue is trying to say. You have free energy at standard conditions, which means celebrate. You know 1 molar. If solutions are involved, you know 1 atmosphere. If gases are involved, and you know 298 Kelvin for the temperature. So all that information comes tumbling out of that itty-bitty naught. When we talk about R, here we're going to talk about the R that has the energy unit. So we're talking about the 8.31 joule per mole Kelvin R. Temperatures obviously have to be in Kelvin. You know that Ln is natural log. And Q is that reaction quotient. And for gases, we can do this in partial pressures. For solutions, we can do it in molarities, which is what the square brackets mean. So I can also rewrite this as the pressure of the products over the pressure of the reactants for gases. And all of these are raised to the power of their coefficients and multiplied by each other. Pure solids, pure liquids do not participate in that expression. So what happens is as Q changes, then we're going to have some issues going on. So at equilibrium conditions, K is equal to 1, and Q would be equal to 1 as well, because that's the one and only moment when Q and K equal each other. And so if you do that, delta G is going to be equal to 0. So we rearrange this a little bit, and we come out with what I've always lovingly referred to as delta G equals minus Ratlink. So I put the minus in there when I say it, minus Ratlink. So delta G equals minus RT ln K. Because when I'm at standard conditions with equilibrium, everything is good. So now, at this moment, when we're using this one, we are at equilibrium. So here the system is at equilibrium, so delta G equals 0. You need to know that. K represents the equilibrium constant under standard conditions. And you should also know that E equals 0. E naught equals 0 at equilibrium. So for minus nunf, delta G is equal to minus NFE, hence the name minus nunf, NFE. That really should look like that, because that almost looked like iron. I probably should fix that. Terms, again, the delta G is just like above, it's the standard free energy. N is the number of moles of electrons transferred. It's what you slash off when you're doing those redox half reactions. And then Faraday's constant, 96,500, 485 if you want to be picky, coulombs per mole of electrons. And E naught is the standard voltage. So this is my connection to electrochem. This is my connection to equilibrium. This is all elegantly connected together. So we've already talked about Big Mama verse 3, and that's what this problem deals with. Find the free energy of formation for the oxidation of water to produce hydrogen peroxide. They were kind enough to give me an equation, and they were kind enough to balance it for me. So delta G naught for the reaction is equal to the sum of the delta G naught of the products minus the sum of the delta G naught of the reactants. That's usually worth a point on the AP exam, even if you screw everything else up from this moment forward. All right, so I like to write it out this way. 2 times the H2O2, so I don't get confused, especially when you're talking about something with H2O2 and H2O. Way easy to get confused. Minus, I've got two things here, so I'll use a bracket. 2 waters. And with water, you need to pay attention to its state, because they may give you liquid, gas, and solid, ice, water, and steam in your vernacular. So you need to pay attention to make sure you pick the right one, because they will try to trip you up that way sometimes. Plus, because that's what sum means, add them together, of the oxygen. Well, celebration moment. Hallelujah, hallelujah. There is an element in here, and I'm talking delta G, so that's a 0. So that's a 0. So this simplifies to 2 times H2O2's value, negative 27.2 kilocalories per mole. Not joules. And that is then subtracting 2 times what's waters, negative 56.7 kilocalories per mole. So 2 times negative 27.2 minus, I'm going to open a paren, 2 times negative 56.7, close paren. 59. So 59 came out nice and even, huh? I'm going to put 0.0 because they put their stuff in decimal places. 59.0, and this will be kilocalories per mole. Now, on an AP exam, they may have given you a conversion factor and asked you to change it to kilojoules, but honestly, I haven't seen a kilocalorie problem in a very, very long time, so I wouldn't sweat it too much. Kilocalories per mole, that's right. I'm not doing delta S. I was thinking I needed that Kelvin in there, but I do not. Okay, now you're about to appreciate why the Kelvin is in there for the joules, because I'm going to multiply this entropy term, I said it right the first time, by a temperature, because the entropy term carries that K in its units, where the others are only in kilojoules per mole. So that's why we have to have that in there. All right, so 298 Kelvin. 1 atmosphere means I'm at standard conditions, so do all those little knots that abound everywhere. And what are we supposed to do? Calculate the delta H, the delta S, and the G, the whole shooting match. AP problem, ESC. Often part A asks you to do one, part B asks you to do another, etc., etc. So shall we do delta H first? Delta H naught equals. Now I think you kind of get the hang of it. So with delta H's, I know that my oxygen is 0, so I'm happy about that. So I'm simply going to cut to the chase on this one and say, okay, 2 times SO3's value. Looking for SO3, looking in the right column, negative 396. I'm going to do units last. Minus, and I only have one entity here, 2 times, what's SO2's value? SO2, make sure you get the hydrogen minus, I'm sorry, not the hydrogen, the H. Brain saw the H, said hydrogen. 297 plus 0, because the oxygen's 0. All right, I'll crunch that in a minute. Let's go ahead and set up delta S, because it's the same song, second verse. 2 times my SO3, so I find SO3, but this time I'm grabbing the S value of 257, and I'm on alert that the units are different here. Minus 2 times, now this one I am going to have to do the whole bloody thing. Okay, so 2 times the SO2 value. Here's SO2, here's 248, here's O2 right there, here's O2. That's why I got to skip it on the delta H step, but I don't get to skip it here, 205. And these are in joules per mole Kelvin. This is going to be in kilojoules per mole. And then when I get those, delta G is going to equal delta H minus T delta S naught. Okay, so let's get the delta H one. 2 times minus 396 minus 2 times a negative 297. Negative 198. What are its units? Kilojoules per mole. So this is negative 198 kilojoules per mole minus 298 Kelvin. I know that much. Oh, look at me putting a degree sign on that. For shame. And now when I get this delta S, I'm going to be in good shape here. 2 times 257 minus 2 times 248 plus 205. Negative 187 kilojoules, no, joules, joules per Kelvin mole. See the J's and the K's and the big K's and the baby K's? There, you can get yourself in a little bit of trouble with this if you're not careful. All right, so I'm going to now, in my head, convert joules to kilojoules, which could be a little scary depending on the time of day. So I'm moving that decimal place 3 places in the proper direction to make a smaller number of kilojoules than I had joules. And look what happens to my units. Cancel, cancel. Kilojoules per mole minus a number times a kilojoules per mole value is a legal arithmetic maneuver. And that mess cleans up to be the negative 198 minus 298, because it was 25 degrees Celsius, that's 298 Kelvin, times a negative 187 divided by 1,000, or you could have just typed it in probably just as quickly. Oop, look, missed a 0. Should come out with negative 142 kilojoules per mole. For a delta G value, those are the correct units, and it is spontaneous. They didn't ask, but I just want you to know. That negative sign right there means it's spontaneous. Okay, that is very, 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 very typical of what you're going to have to do over and over and over and over again working AP problems. So you need to get used to it. That sound you hear is me adjusting my window shades because all of a sudden I'm baking in the sun here. Okay. What else are they going to do to me? Now we want to just calculate delta G. So, well, this is easier. It should have come before that last one. Using the following data, which is all about delta G's, calculate delta G for the reaction. And it's a pretty simple reaction. So delta G of the reaction is equal to the sum of the delta G naught of the product minus the sum of the delta G naught, that's not very pretty, of the reactant. Okay, who's my product? Graphite. Just be sure you pick up the right number. Minus 394 minus, what is the reactant? Diamond minus 397 equals minus 394 minus a negative 397 equals 3. That's a sad little answer, isn't it? 3 kilojoules per mole Kelvin. And why isn't it minus? What went wrong? Did I do the right number? Graphite minus 394. I did minus a negative. Oh, I guess it does come out positive. Double checking. Nope, it comes out positive, so that should read positive. 3 kilojoules per mole. Because yeah, graphite going to diamond is spontaneous. So diamond going to graphite, thankfully, is not. Because, boy, I'd be disappointed if I looked at my wedding ring one day and it was just a whole bunch of pencil lead. So, yeah, that's a typo in the answer part right there. So we are correct. I had to convince myself, but we're correct. All right. So delta G is equal to delta G naught plus RT ln Q. When do I use this? I use this when I am not at standard conditions. We are almost through, so I'm going to pick up the pace just a little bit and get us through this and try to keep this file size under 100 meg for posting, because otherwise it's a pain in the butt to split. Okay, so delta G equals delta G naught plus RT ln Q. And this, if you're using this Q, this is when you use this version, you are not at equilibrium. So one method for synthesizing methanol, CH3OH, involves reacting carbon monoxide and hydrogen gases. Again, nice equation, nice balanced equation. Calculate delta G. Note the lack of naught. At 25 degrees Celsius, so that's 298 Kelvin to you, for this reaction where carbon monoxide gas at 5 atmospheres and hydrogen gas at 3 atmospheres are converted to liquid methanol. So I'm going to use these pressures as my my actual values here. Okay, I hope I have these values handy. Let's see if I do. So I'm going to calculate Q first. So Q, that liquid is not participating. So Q is actually equal to the number 1. So I don't have anything in a product. Pure liquids and pure solids do not participate in equilibrium expressions. So all I can put there is a 1, not a 0, but a 1. And then I can do these pressures though. I would have the pressure of CO2 times the pressure of H2 quantity squared. And that would equal 1 over CO2. I'm sorry, it's CO, not CO2. CO is 5 atmospheres. You can drop the units. Celebrate the moment. K's are naked numbers. Doesn't happen very often in this class. That's 3 atmospheres, but don't forget to square it. So what is that? 9 times 5, 1 over 45. So 45. I love the reciprocal button. So Q, I'm going to put a P on it for pressure, is equal to 0.022. And then delta G naught is equal to the methanol value minus the carbon monoxide value, which means I need a table. Oops, that's a liquid. And I don't have one. Oh no, this is dreadful. Okay, so bear with me. I'm getting a book, because every good nerd has a book close by. Can you hear me flipping pages, desperately trying to race the clock and not make this file too large? Okay, so what am I looking for? Am I looking for G's? Yes, I am. And I'm looking for methanol. Oh, got lucky. Is it in liquid form? Just double checking. Yep. So I find a value of negative 166. And that's kilojoules per mole. And then I look at CO gas. Don't forget that's a minus sign. And I find CO gas at negative 137. And that equals negative 166 minus negative 137. Negative 29. And what's that going to be? Kilojoules per mole. So what else do you want me to do? I'm going to calculate delta G with this information. So therefore, delta G equals delta G naught, which is minus 29 kilojoules per mole, plus 8.31 joules per mole Kelvin, 298 Kelvin, ln 0.022. Yes, that's what my calculator had. I'm bad about missing that first 0 after a decimal point, so I'm double checking that. Okay, that's a mess. I apologize for that, but let's see what we get. Well, we're going to get into unit nightmares here, because this 8.31 needs to be written as times 10 to the minus 3 and throw a K on that kilojoule. Then my mole, my kelvins cancel, so I'm good with that. There's no point in using the calculator until I know my units work. Joules per mole, kilojoules per mole, added to kilojoules per mole. Okay, it's worth it now. So I've got my negative 29 still sitting there in my calculator. Add to it, parentheses, 8.31 second EE minus 3. Again, that's me changing joules to kilojoules so that I can do a legal addition maneuver here. Times 298 times the natural log of 0.02222, however many I want to put in there. I'm going to go ahead and close that paren. I don't think I have to, but just for good measure. And I get negative 38. Oh, thank goodness. I got a little panicked when I had to go look up numbers. Negative 38.4. How many sig figs? 5.0, 3.0. We'll stick with negative 38. Kilojoules per mole. Alrighty then. Okay, again, one more time. When do I do that? I do that when I'm not at standard conditions. So what? The reason I knew that I wasn't at standard conditions would have to have been evaluating the Q versus the K, which they didn't give me. But this is how the problem was put forth in the chapter, so I knew which technique to do. But for you, when you're not at equilibrium or they give you a Q value, they've led you to a Q value somehow, that's when you use that equation. If you have a K value, you come and you use this version, which saves you some time. So here on exercise 15, the overall reaction is going to be 4 iron solids plus 3 oxygens in equilibrium with 2 Fe2O3s. So I've got a couple of solids here. I've got a gas. I know that my entropy is going to drop, right? Because you can see you've got 4 moles of solid and 3 moles of gas going down to 2 moles of solid. Quite a drop. All right, so we want to calculate the equilibrium constant. And they've given us all sorts of information here. So let's just dive in. I may need more room. How much room do I have here? Make some more room. Because I got to calculate a whole bunch of stuff. All right, so you should shut me off and make sure that you go and calculate this too. If I'm going to have to calculate this, what am I looking for? Equilibrium constant. I'm going to calculate K. I need to know T, no sweat. I need to know R, no sweat. I need to know delta G. But look what they gave me to get it. Delta H and delta S. Scratching head, wondering what to do. Oh, I'm going to have to do a big mama and a granddaddy to get all this mess done. Plus use minus rat link. This is quite the orchestration. All right, so delta H naught, just dive in. It's going to be 2 of the Fe2O3 minus, look, element plus element. Okay, at least that was kind. 0 plus 0. All right, so what is the Fe2O3 delta H? So 2 times negative 826 is negative 1652 kilojoules per mole. Delta S naught of the reaction. Shucks, going to have to use all the numbers on this one because those elements values are not 0 because they have electrons buzzing around, so they are not at 0 Kelvin either, so they definitely don't have 0 entropy values. So I'm going to take my 2 times my delta S. Remember, this will also be in joules, not kilojoules as well. And I get 90 minus 3 times oxygen's value. Let me do it this way. What's oxygen's value for S? 205 plus 4 times iron's value, which is 27. $180, and that 2 times 90, minus, paren, 3 times 205 plus 4 times 27. Well, there's not minus signs in there. I don't get as freaked out about it all. Okay, minus, now with the number I'm looking at on my calculator is joules, so I'm going to write it as kilojoules. Minus 543 point, goes right there, kilojoules per mole. And for good form, I should squeeze a placeholder 0 in there. All right, so now what? Now I can get delta G finally. Again, this is very AP-esque. It's just that something would be, this first one would be part A, the second one would be part B, this would be part C, but one would have to know what to do. when they give you H and S and ask about equilibrium constant, you got to run that through G. So there's much to be done here. So that's delta H naught minus T delta S naught, which is equal to minus 1652 kilojoules per mole minus 298 Kelvin times negative 0.543 kilojoules per mole Kelvin. I lost my Kelvin on that, sorry. Equals, okay, I've got my minus 543 divided by 1,000. I'm going to work from the left-hand side of this reaction math backwards because I'm lazy. And I didn't, oh, just divide it by 10 again. For the love of God, McCormick. Can you tell I'm having trouble hitting the buttons right? Okay, so negative 0.543 times 298. So I just got this figured out. That's negative 161. So now minus 1652 minus that negative 161. Do you see what I'm doing? I'm taking, there's my minus 1652 minus as an operator, and then a negative 161.814 is what that all came out to be. Equals negative 1490 and what is that unit? That is in what? Kilojoules. Yeah, because those kelvins canceled. Kilojoules per mole. I'm still not done. I had to get delta G to be able to get to the equilibrium constant. So finally I get to use negative rat link. So delta G naught equals a number, negative 1490. We just figured that out. Minus, which is also equal to minus RT ln K. Therefore, ln K is equal to negative 1490. I'm going to drop the units because K's are unitless anyway. So I'm going to cheat a little bit there because I can. So negative 1490 divided by a negative RT. Delta G is negative, yeah, it's divided by a negative RT, which is equal to 8.31 times the 298. All right, so therefore ln K equals negative 1490, like I said, negative 8.31 times, what's the temperature, 298, equals, okay, so I've got my negative 1490 still sitting there. Divide it by, open a paren, negative 8.31 times 298 equals 0.6. That is not right. Something is wrong. I don't know what's wrong, but something is wrong. That's supposed to come out to 3.69 times 10 to the 6th. All right. That's in kilojoules. Oh, I know what's wrong. My 8.31 is in joules. So that comes out to be 8.31 times 10 to the minus 3 kilojoules times 298. Sorry about that. Goofed that one up. So let's try that again. Negative 1490 divided by the proper numbers now. A negative 8.31 second EE minus 3. Miss the minus. Minus 3 times 298. This is going to be a very different number now. Ah, yeah, 601. Therefore, K is equal to E to the 601. So second ln gets my E on the screen. Grab that baby, enter, and what do we come out with? Overflow. Great. I will have to come back to this because I don't know how to deal with an overflow in the calculator. But I can tell you that the number's ridiculous. It's supposed to be 10 to the 261, which is crazy anyway. We have to figure out what to do about that overflow in the calculator. I've never encountered that error before. But it makes sense because this is a gargantuan number anyway. But you get the method. I'll have to figure out, talk to some math teachers and figure out what the heck's going on with that. Okay, so let's see if we can push through this last couple. Or last one, actually. The Gibbs equation can also be used to calculate the phase change temperature of a substance. During the phase change, there again, that is that equilibrium between phases, so we know that the value of delta G is 0 when you have an equilibrium situation. It's really just like what we did earlier in this unit with the entropy and enthalpy. Okay, so here's what we know. We know that delta G equals 0, and it also equals delta H minus T delta S. So therefore, we can say, okay, that means that if I took the delta H over, it would be minus delta H equals minus T delta S. Therefore, we can drop the minus sign on both sides and say delta H simply equals T delta S and solve for T. Now, this is an approximation. This is not an absolute because S is temperature dependent. So we're always going to have a little bit of wiggle room in here, but it is a pretty good approximation of what the temperature would be. So T would equal delta H divided by delta S. Watch your units. That's 44 kilojoules divided by 0.1188 kilojoules per Kelvin, which makes sense if I want a Kelvin. And it really should be per mole in both cases, but that's going to cancel out. All right, so what do we get? 44 divided by 0.1188, 370. No overflow this time. A normal answer, 370 Kelvin. And we do this a lot. This is something that's easy to do. At equilibrium is your friend because you know that delta G naught is 0, and then you set the equation so that you can solve for T when your terms drops out, basically. All right, so a little bit of summation here at the end. Summary of the free energy business. We have already pretty much ingrained into you that delta G, when it's positive, means it's a non-spontaneous reaction. When delta G is negative, it's a spontaneous reaction. So these are all the conditions. If you want to memorize them, feel free. I'm too lazy for that. I just figure it out using delta G equals delta H minus T delta S. But these are the relationships that you really should know. These are very important. This is multiple choice points like crazy. When delta G is 0, E is 0, and K is equal to 1. Now notice they're not knots on here, so these are thermodynamic conditions. So when delta G is negative, that means the products are favored. You're making product, the reaction's going forward, in other words. And E is positive, because that's what a spontaneous battery has, is a positive EO cell. And then turn all of that around. If delta G is positive, then it's not spontaneous. You're going in the reverse direction if an equilibrium is present, and you're going to have a negative E. And then these graphs also show up sometimes in the multiple choice. So we want to take just a minute and talk about these graphs. When you talk about a reaction where we evidently have this A in equilibrium with B reaction, the fraction of A that has reacted at time 0 is going to go down, 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 down. When it bottoms out and it starts going back up this way, which is what we see over here on this graph, it's starting to go back up that way, that minimum there is where you have actually achieved your delta G. At any point along this curve, your delta G can be computed by doing the slope of the tangent line at any one of those points. So the change in free energy to reach equilibrium beginning with 1 mole of A at a pressure of A equals to 2 atmospheres, what this first graph is showing us. Then the change in free energy to reach equilibrium, if I begin with 1 mole of B and go the other direction in this equilibrium, and I go back this way. So this is forward, this is reverse. But either way I get there, I get this free energy profile for this system, whether I came at it from that direction or whether I came at it from that direction, it bottoms out. And where it bottoms out, that's where the equilibrium occurs. So if we have actual numbers on this graph, we can pick those numbers up and we can actually calculate the K value, products over reactants raised to the power of their coefficients. So each point on the curve corresponds to a total free energy for a given combination of A and B. Now, the last thing I'll say about delta G is that delta G is tied to the amount of work a system can do. So the value of the free energy is not only useful for defining spontaneity, it's also useful if in understanding the maximum amount of work that is produced or required by a system at constant delta G. So delta G equals that maximum amount of work. So when the reaction is spontaneous, that's a good thing because delta G is the energy available to do that work, like moving a piston in a car engine, or flow of electrons in an electric motor. But when delta G is positive, it's non-spontaneous, then it represents the amount of work needed to make the process occur. So it's like using your cell phone battery, recharging your cell phone battery. So thank you so much for your kind attention. I hope you found this somewhat helpful. I promise you will understand more and more and more. The next step that you should make is to listen to the recordings on the thermodynamics essays before we go back to the math, because the essays is where all the concepts are located. It's where the real understanding happens. It's where we're going to talk energy, 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 energy. I'm going to teach you to write about energy, energy, energy for maximum points on the free response. And then I also want to review you on the math side of things. You certainly are not expected to listen to everything, but I hope you listen to something. Until next time, thanks for your kind attention.